You're much welcome at this session where I want to talk about synthesis, storage, and release of norepinephrine. Then we shall see different receptors and the function it exerts when found in different locations. So as we begin, we remind you to subscribe if you haven't and like the video that we can continue to be growing. So we want to look at the synthesis. How is norepinephrine synthesized? How is it stored? Then how is it released to bind to the receptor? And after binding, how is it degraded to within the synaptic cleft? And to begin with, you're going to see that this synthesis begins with the transportation, whereby in the cytoplasm we have tyrosine, and this tyrosine depends on sodium, that when sodium is moving inside, tyrosine also, this is a secondary active transport known as sodium tyrosine transport, which enables tyrosine to enter into presynaptic neuron. This is the presynaptic, this is the synaptic. And after tyrosine entering, it is hydroxylated, whereby we add a hydroxyl group, and after addition of the hydroxyl group by an enzyme known as tyrosine hydroxylase. So tyrosine hydroxylase enzyme catalyzes the addition of the hydroxyl group on tyrosine to form DOPA. Here we form DOPA, which is dihydroxy methyl phenylamine deoxyhydrox. This is dioxyhydroxyphenylamine. Phenyl is phenylalanine. Dihydroxyphenylalanine is the DOPA. So DOPA in full is dihydroxyphenylalanine, which is formed after addition of this hydroxyl group to tyrosine by tyrosine hydroxylase. And this step is the rate limiting. This one is rate limiting step. This is rate limiting step in the synthesis of norepinephrine. After forming DOPA, then DOPA is oxidized to, it is decarboxylated to dopamine. This one is decarboxylated to dopamine. Decarboxylation means loss of carbon dioxide, and this carbon dioxide is removed by an enzyme known as decarboxylase. So decarboxylase enzyme is the one that is catalyzing the removal of carbon dioxide from dihydroxyphenylalanine to form dopamine, and this dopamine formed is the one that is converted into norepinephrine. This one, dopamine, which is formed, is converted into norepinephrine, abbreviated as NE, and after being formed, this one marks the end of point number 1, which is synthesis. So point number 1 is synthesis of norepinephrine, which we have done in the presence of two enzymes, the hydroxylase and decarboxylase, whereby decarboxylase leads to formation of dopamine, which can be converted to norepinephrine. And after forming norepinephrine, we are going to see shortly that this dopamine which is formed and DOPA and dopamine which are formed can be degraded by MAO. These ones can be degraded by MAO, whereby MAO is known as monoamine oxidase. Monoamine amine. So they are oxidized by MAO and excreted in urine. So MAO can oxidize dopa or dopamine and to inactive metabolites, to their inactive metabolites, and these inactive metabolites are excreted in urine after being broken down by monoamine oxidase. Then this norepinephrine is going to lead us to point number 2, which is storage, whereby this norepinephrine is transported into the synaptic vesicle by amine transporters. We're going to see amine transporters enabling the entry of norepinephrine inside the vesicle. So we're going to see norepinephrine entering into the vesicle by transporters known as amine transporters, and then it is stored. So this one is point number 2, which is storage in the vesicle. And this storage, these transporters can be inhibited by recepin. Recepin is a drug Recepin is a drug which inhibits transportation. This one inhibits transportation by inhibiting amine transporters. So this one inhibits amine transporters so that this norepinephrine formed cannot enter into the vesicle for storage. After seeing how they are stored and transported and stored in the vesicle, the third thing is to look at release. Can now talk about release and how are they released. Under release, we are going to see that this norepinephrine is released by upon entry. We know that in the cleft there is always calcium ions, and these calcium ions, when this norepinephrine enters and this cell becomes depolarized, whereby inside it becomes positively charged due to the entry of sodium, it causes opening of the calcium gated channels. This is calcium voltage gated. And this opening of calcium voltage gated channels will enable entry of calcium into the presynaptic neuron. And when calcium enters into the presynaptic neuron, it causes a voltage, or it creates an electric power. And this voltage or this current and contraction is produced by the entry of calcium ions in the presynaptic neuron causes contractions, which leads to the fusion or movement. This one moves, the synaptic vesicle moves, and after moving, it comes and fuses with the membrane, with the presynaptic membrane. After fusing, it will release the neurotransmitter by exocytosis. So after fusing with the membrane, it will release this neurotransmitter, that is norepinephrine, is released by this process of release is by exocytosis. This is by exocytosis. Upon entry of calcium ions, which causes an electric current and contractions leading to the fusion of the synaptic vesicle with the presynaptic membrane, leading to the release of norepinephrine by exocytosis. And we're going to see that this release is inhibited by the drug known as, this drug is known as guanethidine Norepinephrine is the drug that inhibits the release of this norepinephrine by exocytosis. So that is the drug that we can apply, which is indirect acting antagonist, adrenergic antagonist. After the norepinephrine is released, the step number 4 is going to be binding. Step number 4 is binding, whereby it is going to binding to receptors, whereby receptors can be alpha 1, beta 1, alpha 2, beta 2, and beta 3. And after binding, so we are going to see this norepinephrine, after being released, comes and binds to its receptors. This one also comes and binds to the receptors on the postsynaptic neuron. It binds to the receptors, and it depends on which receptor. If this receptor is like alpha 1 being G2, this is G-coupled receptor, and when it is G2, we see it activating second messengers, that is IP3 and DAG. IP3 causing increase in calcium ion intracellularly, and this one causing phosphorylation, hence bringing the response. If this one binds to maybe beta 1 is GS, so it will lead to increase of cyclic AMP. If it binds to this receptor known as alpha 2, because alpha 2 is found in the presynaptic membrane, so and alpha 2 is GS, this one is known as G inhibitory, G coupled receptor, but which is inhibitory type, and for it acts by decreasing CAMP levels. And when it decreases CAMP levels, it inhibits release of norepinephrine. So this one is the one that inhibits release both acetylcholine and norepinephrine by reducing CAMP levels within the cell, because it is inhibitory. So we are seeing when it binds to receptors, the response depends on the type of receptor, which we are going to see shortly. Then after binding, the remaining norepinephrine, we have seen some come and bind on the photoreceptors, or what we call presynaptic receptor, that is alpha 2. Another one, now we are on point number 5, which is degradation, or we can call it, you see, we are seeing how is it utilized or utilization after binding. So we are seeing some of them bind to the autoreceptors to modulate or to inhibit further release. After inhibiting further release, this one inhibits further release. After inhibiting further release, we are going to see the remaining norepinephrine can be transported back in the presynaptic, and by it uses this transporter, can be transported back in the presynaptic neuron, and after being transported, it can enter back into the vesicle and reuse it. And this transporter is known as norepinephrine reuptake transporter. So this is reuptake transporter, and we're going to see this norepinephrine reuptake transporter is inhibited by many drugs. This reuptake of norepinephrine is inhibited by drugs like cocaine. Cocaine is a drug that inhibits reuptake of norepinephrine. We are going to see serotonin, norepinephrine reuptake inhibitors also doing that role. We are going to see even another drug like imipramine. So these three drugs inhibit reuptake of norepinephrine back into the presynaptic neuron. Apart from this norepinephrine being reuptaken into the vesicle and released again, another way we can also oxidize it. It can undergo oxidation by marrow and it is excreted. It is excreted in urine. So this is the degradation or reuse, whereby we have seen A is the binding to the alpha-2 receptors, B is reuptake, then C is going to be this norepinephrine here. It can also be degraded by an enzyme known as COMT, whereby COMT, that is catechol or methyl transferase, removes the methyl group. This one removes methyl group from norepinephrine and it forms epinephrine. So this is another way, which is C. We can reutilize this norepinephrine by COMT, whereby this COMT is responsible for removing a methyl group from norepinephrine to form epinephrine. And we shall see different drugs which target COMT and those ones that target or inhibit MAO. We shall see them as we move on. So after seeing degradation, this one marks the end of synthesis, storage, and release of norepinephrine, whereby we have seen synthesis, whereby we need tyrosine hydroxylase to form DOPA, and then DOPA is decarboxylated to dopamine, which is converted to norepinephrine, and this norepinephrine is transported inside the vesicle by amine transporters, which are inhibited by recepin. Then we went to point number 3, which is release, that upon entry of calcium ion via voltage gated channel, it causes electric current or voltage current that causes contractions of the vesicle to fuse with the membrane, leading to release of norepinephrine by exocytosis, and we saw it is inhibited by guanethidine. Then after being released, it binds to receptors, bringing about different cellular responses depending on the receptor. Then we have seen how it is utilized in different ways. One, binding to the alpha-2 receptor to inhibit further release. Another one being reuptaken by norepinephrine reuptake transporters inhibited by cocaine, serotonin, norepinephrine reuptake inhibitor, and impramine. Then finally, we have seen even this norepinephrine is methylated. It is also methylated. So this is what we can discuss under this process. The last part is the functions after binding to the receptors. And we have to remember that this is sympathetic part of autonomic nervous. So sympathetic, it is for emergency situations, which we call fight and flight. So as we are looking at the functions, you have to put and you meditate what happens in case you see a fearless lion, or when something is scaring you, how does the body react? For example, when someone scares you, we're going to see reactions which is alpha 1 and beta 1. And we're going to see this alpha 1, which is located majorly in the CNS, in the postsynaptic neurons of the central nervous system, and sometimes found in the smooth muscles of the prostate and the blood. And alpha 1 and beta 1, these ones are stimulatory. Why I put them together is that for them, they are stimulatory. For them, whenever norepinephrine binds, for them they are stimulated, which is different from these alpha 2 and beta 2. For alpha 2 and beta 2, for them they are inhibitory. These ones, we are going to see this alpha 1, alpha 1, yes, they are stimulatory. Then these ones are inhibitory. For them, they inhibit. So the responses which come in this results into inhibition. Then beta 1, because the heart is 1, we find beta 1 in the heart or cardiac. And sometimes we can find it in the juxtaglomerular apparatus of the kidney. Whereas alpha, because the lungs are 2, beta 2 is majorly found in the lungs, that is the bronchus, but still we can find it in the GIT, in the bladder. Even the eyes can be supplied by beta. So beta 2 is widely distributed, whereas alpha 2 for it is found presynaptic. In presynaptic neurons or nerves, the way we have seen it here, and it is inhibitory. Whereas beta 3 is less, but is found in adipose. This one can be found in adipose and sometimes urinary bladder. We can find beta 3 receptors. And whenever norepinephrine and epinephrine binds to alpha 1 receptors in the CNS, it's going to lead to the reactions of fight and flight. So we are going to see this one is going to stimulate or to increase activities. For example, in the prostate, it will increase contraction, increases contractions of the muscles. But this beta 1, which is found in the heart, it is also responsible for causing increased contractility of the heart. It causes increased contractility of the heart, and this one leads to increased heart rate, and so there is increased heart rate and contractility of the cardiac muscles when stimulated, because we said for these ones are stimulatory, whereas these ones are inhibitory. And whenever it goes to the juxtaglomerular apparatus of the kidney, for it causes release of renin. It causes release of renin. And this renin is the one responsible for triggering RAS, which is the renin angiotensin aldosterone system. Then when alpha 2 is, when the epinephrine binds on alpha 2 receptors, this one inhibits norepinephrine release, and sometimes even acetylcholine. Then another effect, that is, for if we go to beta 2, we are seeing for them they are inhibitory. And because it is inhibitory, we are going to see when it goes to the bronchus, it causes bronchodilation. When it goes to the GIT, it decreases the motility, decreases GIT motility and secretions. And when it goes to the bladder, it causes relaxation of the detrusor muscles and the trigone sphincter. When it goes to the eye, if it is found in the eyes at the ciliary muscles, it causes relaxation leading to mydriasis. Leading to mydriasis, that is widening of the pupil. When it is in the uterus, it causes relaxation still of the uterus. When it is in the muscles of the penis, it can also lead to relaxation, so ejaculation cannot occur, or it is inhibited. Then in the adipose, It triggers lipolysis. It triggers lipolysis, that is breakdown of fats. So these are the different functions, because when there is a fierce lion in front of you, or someone has scared you and you want to run, one thing, the heart contractions or the heart rate should increase so that much of the blood is pumped to enable you to run. And when you want to run, meaning the airway should also be open. The airway should be open. And when the airway is open, you are able to increase breathing rate. And when breathing rate increases, you can also be able to run. And then you have to open widely the eyes and so forth. Then you cannot urinate or go to a short call when something is running after you. So thank you so much for learning until the end. We thank you so much.